Hey guys and girls. You might be wondering why am I outside on this beautiful day here with this cup of water when I could be inside playing video games and watching YouTube. Well, the reason is because of this black rock here. This black rock holds, you might not believe it, but it holds a lot of energy. And that energy was from back from the dinosaurs when they lived. And so when they decayed, like for instance trees, got compacted, really dense, and then store their energy inside things like these rocks, or petroleum. But my question is, where does that energy come from? Now, a black rock like this can release enough energy to power my house. Not alone, of course, but if you get enough of them, you can heat up some water and then use that water to turn a turbine and everything. But where does it get its energy? Now, obviously, it gets its energy from the dinosaurs that died and made this. But where did they get that energy? The answer to that is right up there in the sky. That's right, the sun. Now, basically everything on Earth gets its energy from the sun, directly or indirectly. Like, for instance, grass absorb the sun's energy and make food for it. And then, using photosynthesis. Then cows come along, eat the grass, and they gain energy from the grass. And then I come along and eat the cow and gain energy from the cow. And so it's all one big happy cycle. Now the question I'm interested in is, how much energy does the sun put out per second? Let's start calculating. So the sun fuses about 620 million metric tons of hydrogen every second. And for about 100 grams of hydrogen, 993 grams of helium is created, leaving 7 grams turned into pure energy. So we just multiply 620,000 by 7, and we come out with 4,340,000 metric tons transferred into energy a second. So how much energy is that? So if we take that number and multiply it by how much energy is given by 1 gram, which is about 90 teranewtons, using the formula equals mc squared. But how much is it in metric ton? Well, it's about 1,000,000 grams. So we just multiply that by 1,000,000, and then multiply that number by 90 teranewtons. And then we should come out with 390,600,000,000,000,000 teranewtons or seconds, or in other words, terawatts. So that's quite a bit of energy. But, seeing as how the sun's so far away, the energy ends up spreading out into a sphere around the sun, and basically we get less and less of that energy the farther away we are. Seeing as how it takes light 8 minutes and 19 seconds to get to Earth, we're pretty far away. So, just how much of the sun's energy hits the Earth every second? So, if we calculate the distance from the sun to the Earth, we can find a sphere and see how much energy is spaced out from for every square kilometer. So we use pi r squared and the radius of the Earth to the Sun, which is 149,600,000 kilometers, and we come out with 2.91257585 times 10 to the 17th square kilometers. After calculation, we come out with 0.0013888862 terawatts per square kilometer. Now let's find out how many square kilometers the sun hits with energy. So we'll take the radius of the Earth, which is about 6,371 kilometers, and then we'll use the formula pi r squared. Now let me tell you why I'm using that formula instead of the formula for a sphere. Now the reason I'm not using the formula for a hemisphere is because the Earth is curved. And so the sun's energy comes in straight lines.
And so the curving comes into play. It doesn't come in all directions at 90 degrees to the Earth's surface in all places. It comes in at angles, like that. So, in total, it's as if the sun is hitting a circle with that amount of energy, not a sphere. So, the same thing is apparent when we hold a piece of paper. So I hold it straight on, it looks like the full piece of paper, right? But when I tilt it, like that, it looks a little bit smaller. Like the amount of area that we see that is apparent to us is smaller by the amount of tilt. And so the same sort of tilt is inherent on the Earth's surface with the sun hitting the Earth with energy. So we come out with the area of a circle and not the area of a hemisphere. Now that we know why we're using pi r squared, we can figure out how much area the Earth has apparent to the sun, which is about 127,516,118 kilometers squared. So, if we go ahead and multiply that by the amount of terawatts per square kilometer, we come out with a huge amount of energy. And so that amount of energy is 177,102.328 terawatts. That's the amount of energy that hits the Earth, the sun supplies for Earth. And this is, of course, not paying attention to significant digits.
But not all of it gets down to where we are, mostly because of our atmosphere. Now, of course, we need the atmosphere to survive. We need to breathe air and everything. If there were no pressure around us, we'd just explode. But it ends up reflecting about 6% by the atmosphere alone, and then 20% is reflected by the clouds. Then about 16% is absorbed directly by the atmosphere, and only 3% is absorbed by the clouds. That leaves about 55% left. Now, eventually, when all that energy gets down to the surface level, 51% of that is absorbed, and then another 4% is reflected off the surface. So, the Earth basically absorbs at the surface level 51% of that. But still, that is a lot of energy. Anyway, leave new questions in the comments below, and I'll try to make another one as soon as I can. Thanks for watching.